So hi, today I was supposed to talk about quantum cryptography, but I was expecting actually a pretty much smaller audience. I was prepared on a blackboard. So I guess I switched to a talk that I actually gave recently on a different project. Actually, so quantum cryptography was my thesis project. So I passed most of the time on it. So this is the smaller one, actually. I spent less time, but it's actually nevertheless very interesting. So first, I would like to thank for the invitation of coming here. I'm pretty happy to. It's my pleasure to come visit Agra and his institute. Okay, in a standard scenario, when we refer to a reference frame, we actually mean that it's a classical object. It's something that you can use in repetition to either perform a measurement or, to do any other operation with it. And you can share with other people. And fundamentally, that object will not degrade, okay, for fundamental reason, except if you decide to rip it or burn it or something. But it turned out that in quantum mechanics, well, you can have some quantities, some classical quantities that encode in a quantum state, and that if you use a quantum state to perform some operations, some measurements, then what's going to happen is there's going to be some back action map that's going to act on the quantum reference frame, and that's actually going to modify the states, and it's going to reduce the quality of that reference frame. So in this talk, I'm going to concentrate on a really specific scenario of relational quantum mechanics, where we actually use a quantum reference frame that contains information about a direction in space. Okay, so there's one thing that's important to know is that a lot of people are interested in finding how to quantify how good, the quality of a quantum reference frame. In this scenario, it's a really restricted scenario. We actually establish all the quantities that are of interest to qualify the qualities of our reference frame. So by studying something much simpler, we hope that we're going to be able to construct a more general theories for reference frame. Okay, so this is joint work with two of my colleagues from the University of Waterloo, which is Anna Sheridan and Martin Lafollette, and Stefan Barnett from the University of Sydney. Okay. So, on the first part of my talk, it's going to be much more mathematical. So I'm going to give a polynomial representation for any map that's covariant with respect to what we call an irreducible representation of SU2. What this means is if I have a map, a quantum map, that's invariant on the rotation in space, then I will have some nice form for it, some nice way of writing it in general. And it's going to help me. This one will be, with this one, it's going to be easier to analyze than the scenario based on the scenario I'm interested in. And I will be able to study the dynamics of the quantum reference frame. Okay, so in the second part of the talk, I will introduce what I mean by moments, quality, and longevity of quantum directional reference frame. And then I'm going to conclude with some example where actually what I'm considering can be useful for calculations and analysis. Okay, so let's go to the first part, which is the classification of rotationally invariant maps. So, what I mean by SU2 is actually all the set of 2x2 complex unitary matrices that have determinant norms. But it turned out that set is actually isomorphic up to a sign to the group of space rotation, so rotation in space, right? And then when I talk about representation of SU2, I'm actually talking about a rotation in vice versa. So I will also consider what I said earlier, irreducible representation of SU2, okay, that act on a specific space of dimension 2j plus 1. Now, the fact that I restrict myself to reducible representation in physics, it does mean that I actually consider rotation of a spin j particle. And when I'm talking, okay, so basically SU2 is a Lie group. It has a corresponding Lie algebra. And this Lie algebra is generator Gx, Gy, and Gz. Well, actually, when I'm talking about those generators, I'm actually just meaning the angular momentum operator in the x, y, and z direction. Okay, and those angular momentums are the operator that follow the commutation relations that were used to in quantum mechanics. So for those who know quantum mechanics. So what do I mean by covariance with respect to SU2? Suppose that a map chi is covariant with respect to SU2. Then what it implies is that if suppose I have a density matrix of my spin j, and then I apply rotation on it in the space. Okay, so one of the representation of SU2. And then I apply my map chi. It's the same thing as on that density matrix. I would have applied chi first and then the rotation. And that should be true for all of them.
So now let's look at the term the new term, the new representation that I'm proposing. But let's first define some map that I call zeta, which is actually just as if I apply one of the generators that I was talking about at random. So I apply one of the angular momentum on my density matrix, like uniformly. And then this is just a normalization constant. Then what I say is that any map Z, which is covariant with respect to EREFs of SU2 that act on some space of dimension 2j plus 1, has a polynomial form with respect to the map zeta. So just chi can just be written like this. You see the degree of the polynomial is here is 2j. There's actually 2j plus 1 independent parameters. Okay, so the coefficient qn, which are actually must be all real. So what I mean by zeta circle n is just the composition of n times the man zeta. Okay, so how do you prove this? Technically, to prove that zeta, okay, so a map that has the form that I just gave, if it can be written as a polynomial of the man zeta, then it must be covariant. Why? Because the man zeta is covariant. And you can show that by direct calculations. Now, I guess the details are not that extremely important, but if you write that man zeta in a certain, that's what we call the trivial representation, then that, what we call a superoperator, can be represented as actually the sum of 2j plus 1 linearly independent matrix. And it's possible actually to show that any covariant matrix has only 2j plus 1 independent parameters. So basically, this is all like the mechanism of the proof. Okay, so the open question there related to such a form
is simply that suppose that you consider a map that's covariant over a different Lie group. Okay, a different group. Do we have a similar form or not? Like, is there a generalization of that theorem? And the other question is, what are the restriction that we have on the Q-mesh parameters? I mean, we can prove that they are real, but because quantum map must be actually a completely positive transposition map, then what's all the other restriction on the parameters? Okay, so let's do something more physical. So now we have a polynomial representation for covariant map with respect to rotation in space. What can we say about the dynamics of quantum reference frame? So first we need to define what I mean by a quantum directional reference frame. So consider the density matrix, the states of a spin jet. So I just say that it's represented by rho j. So the index 0 here is just to say that it's my initial state. I'm going to actually use my quantum reference frame a couple of number of times, and every time I use it, I'm going to increase that index 0 to 1 to 3. Now, one of the properties that we want on my quantum reference frame is that it depends only on a certain direction in space. Let's call the direction in space n hat. Then, since the quantum reference frame only depends on the position n hat, sorry, the direction n hat, then any rotation around n hat, well, must not change that state, the density matrix. So, what we can say is that the state rho j0 must be invariant on the rotation about the n axis. And this implies directly that rho j0 can be random. Is diagonal in the basis that's constitute of the eigenvectors of the operator, the angular momentum operator in the n hat direction. Okay, so let's look at the scenario we're considering. So we have some quantum reference frame. We start with a certain state for a quantum reference frame, and then we have a reservoir. The reservoir is constituted of many identical states that are uncorrelated one to the others. We also assume that each of those states has a dimension d, and that they're actually invariant on their rotations. Now, what we do is we take one of the subsystem of the reservoir, we join it with the quantum reference frame, and we apply some map chi. So chi is choose the way you want with one restriction, that it must also be invariant, covariant with respect to SU2. So you apply that map. That map can represent your measurement. It can represent any operation that you want to do. Maybe you want to implement some gate, some transformation on the reservoir system. And then your chi just represent how this transformation is performed. Now, after you did this, what we do is we're just gonna, like in our scenario, we're just gonna consider the new states of the quantum reference frame, which is obtained just by tracing out, taking out, getting rid of the state of the reservoir. Okay? And this actually gives you a way of writing out what is the back action map that acts on the quantum reference frame. That's I call actually Z. So how does it look? So after we did that with the first state subsystem of the reservoir, well, then we can, with the new state for the quantum reference frame, we can take just the second subsystem of the reservoir and then reapply the same map. And then getting right again, discarding again the subsystem of the reservoir, obtaining a new state, and doing that again and again. After that, we're going to define quantities that are going to quantify how successful was the operation that we wanted to do. That was what Chi was supposed to do. Okay, and our goal would be to study that quantities, how that quantity decrease with the number of time that we. So I said that I was making two assumptions, which is that Z, Chi is covariant with respect to SU2, and that the state of the subsystem was invariant under space rotation. Well, this actually implied that the back-action map Z that's applied on the quantum reference frame is actually also covariant with respect to SU2. Okay, but by the way, just when I wrote here that this was actually invariant, I also mean it's the same thing as a synonym to covariant with respect to SU2. Okay, so now the fact that the map that's applying the quantum reference frame is covariant with respect to SU2, it implies that all the new quantum reference frame state that we're going to have will also be diagonal in the basis that's given by the eigenvectors of the angular momentum in the n direction. Remember that the initial state that we had this property. Now all the state that we're going to have this property here. So basically, the problem that we're considering is actually some walk around so we're considering some walk on the eigenvectors of the angular momentum operator in that. Okay, so there is previous work that made reference to that scenario. The previous work that was considering such thing was they had a pretty restricted. They considered only one specific joint operator Z. Right now, in the discussion I have here, is like do any kind of operation that you can make that's rotationally invariant. And they also restricted themselves to reservoirs that are made of spin one off. Well, we made no such assumptions. And they had a really specific way of quantifying how the quantum reference frame was good. Like the quality of the quantum reference frame was quantified by a function that was fixed. Here we're gonna consider any function that actually can quantify the quality of a reference frame. Okay, so what do I mean by quality function of a reference frame? So the quality function is used to quantify the ability of a reference frame to perform a certain task. So it's quite general. The only assumption that we make is that this function does not depend on a particular directions, the particular direction of an act. So it does mean that the function f, the quality function, can only depend in a scenario on the eigenvalues of the quantum reference frame. Okay, so there's an equivalent set to the eigenvalues of the quantum reference frame. It's what we call the moment. So just so that you know, rho j has actually 2j plus 1 eigenvalues. Of those eigenvalues, well, they're actually not independent because the sum of them must be 1. But one way, so this gives you a set of parameters that's equivalent to this set of parameters here.
So what I mean by the L moment is the trace of the state of the quantum reference frame with the angular momentum operated in the n-hat direction to the power L. The function k, well, it's just sufficient just to study the evolution of those parameters. So that's what we're going to do. So just by doing linearity in quantum mechanics, it's actually just possible, a really simple argument to show that if I take the quantum reference frame after I use it k time, right? And I consider this L moment, so that's the L moment of the quantum reference frame at the k time. Then it's a linear function of the moments, all the moments of the quantum reference frame at k minus 1 time, so just one step earlier. And now the question, well, I mean, so one of the interests is to calculate what those coefficients are. Now, one point is that the theorem one, the first theorem that I proved in the first part of the talk, basically nearly automatically imply that many of those coefficients are going to vanish. So suppose that we take L as even. Then all of the moments that are higher than L, all the coefficients that correspond to our L, that's I here. When 2I is higher than L, actually, then all those coefficients is going to vanish. And all the coefficients that correspond to odd numbers is going to also vanish. And if L is odd, it will know that all coefficients that correspond to an index that's higher than L and also an index that's even will vanish. So it's quite simplified, the recursive equations. And we're going to see later in the example like that it can actually be quite useful. It's also useful, this term that I just gave, it's also useful to prove something about what I call longevity. Okay, so I will first define, what I mean by this. There is an interest to know how many times we can use a quantum reference frame before its quality function get below some threshold that we set up. And this is not how many times that it takes, it's called the longevity. Now, in a really specific scenario that was studied earlier, it was shown that actually the longevity scale as j squared, on the order of j squared, which is actually, j is just the size of your quantum reference frame. So, actually, the j square factor was quite surprising, and well, not that quite surprising if you know quantum mechanics, but from a classical point of view, it can be surprising, because when we say that the longevity scale as the square of the dimension of the quantum frame, then it's counterintuitive to the idea that if I take my quantum frame and I separate it in many different systems, then using all those little systems separately is as good as using the whole system. Okay, it's what we call so integrament without locality or something like this. Anyway, so some people say it's some sort of quantum effect that a joint measurement can actually perform there. So one other thing that happened is that Poulet and Yard, so the two other people actually showed that this effect is actually quite sensitive to imperfection in. So I was assuming that the reservoir was rotationally invariant. It turned out that if it's not perfectly rotationally invariant, then that factor is actually quite sensitive to those imperfections. Well, what I want here is just to put the theorem that's going to englobe the idea of when actually it happens
that we observe that J is a proof factor? What are the conditions that it can actually be observed? Okay, yeah, just a little details. So they actually show that the longevity of the quality function was scaling as G squared. However, they really had a specific quality function when they studied this. But in our scenario, we're considering any quality function. We're considering a really more general set of possible functions. And it turned out that the scaling can be quite arbitrary, because I could build a quality function the way I want in terms of the moments. And the term I'm going to give in the next slide is actually about the longevity of the moment. The only really fixed thing that does actually mean something. Okay, so the main point now is that what we are doing is we're considering different quantum reference frame. So we're increasing the dimension of the reference frame. And then we're applying on a map chi that depends on the dimension of the dimension of my quantum reference frame. And then I'm trying to perform some task with it, so it can be defined quite arbitrarily. But every of those quantities can define on the dimension of my quantum reference frame. So I just need to put conditions on those relations, on the dependence between the states, the map that I'm considering with respect to the dimensions of my reference frame. And the three conditions can be termed in a physical way like this. So the first one is that the maps that I'm considering, the map chi's, are actually preserving angular momentum in the x, y, and z direction. The other condition is that the map chi that I choose in function of j actually does converge, not in a bad, well, it does converge in some nice way. Not too nice, but nicer than going everywhere. And the other condition is on my quantum reference frame. It means that actually there's support on well, actually I said that my quantum reference frame is the spin j in a certain direction, but for those who know quantum mechanics, a spin j can be pointing okay, so a spin j is going to have, okay. There is actually, okay. So the spin j has angular momentum in the n hat direction. Okay, it has discrete angular momentum from minus j to j. So what I'm saying is actually that states must have some support in the j states. Okay? And basically with those conditions, when you can observe a longevity that scale as j squared. And the proof is based on the previous theorem that I gave. Okay, so let's start, let's go over an example. Suppose that we consider a reservoir a spin 1/2. And that each of the spin are indeed pointing with the n hat direction or in the other direction than n hat. Okay, but they have the same probability of being in either direction. Now, the goal is to use a quantum reference frame, so a spin j, in the direction of n hat, to guess in which direction each of the spin 1/2 is. If there's pointing with or it's parallel or anti-parallel to n hat. Okay, so there exists optimal measurement chi, okay, which is actually just a projection into the subspace
the total angular momentum subspace of j plus 1 half and j minus 1 half, but okay, that's a detail that you can make. That's going to give you, so this is the best measurement that's going to give you the best probability of guessing if the spin 1 half was parallel and anti-parallel. And then you can define a quality function as the probability of your guess to be right. Okay, so this is just the formula, this is the equation corresponding to this. So it turned out that this probability of guessing is just a function of the first moment. And the first moment, if you follow theorem 2, well, it just depends on the first, like the first moment of the quantum reference frame at the k step only depends on the first moment of the quantum reference frame at the k minus steps with a constant. If you repeat that step k times, well, you simply get the first moment of the quantum reference frame of the k step is equal to the first moment of your initial quantum reference frame multiplied by a constant to a power k. And actually, it turned out that calculating that constant is actually pretty easy. So, like from this, we get a really nice way of seeing how that, how the function behaves exponentially with that factor here. Okay, so we can generalize these ideas. We can go to consider, suppose we have a spin 1, and that we're actually checking if it's parallel, anti-parallel, or perpendicular to the n hat direction. And we can use the same technique. We can define the quality function as the probability of guessing it right. And then we can see that the probability function is going to depend on the first and the second moment. We use theorem 2, the recursive equation that we get. And actually after that, the equation is not that complicated, but I'm going to plot it on a further graph. But it's a nice way of making the calculation. It can be quite more involved with all those tricks. Okay, so here's a more interesting example. Suppose that you want to do, you want to perform a certain gate on one of your states in your reservoir. So, and suppose that gate is just this phase gate here. To implement a phase gate, you need to define a direction in space, and this is where we actually use the quantum reference frame for. Okay, and it's actually impossible to implement a phase gate without a quantum reference frame, without making errors. So now you can define the quality function the way you want. Some people like the gate fidelity to perform gates, so you take the equation, take it from a textbook, and then you choose your chi function, so the kind of operation that you're going to implement to perform your gates. I'm just going to discuss about one, I guess. We don't have to go over 3 different examples here. Suppose that between your spins, suppose that you have between your quantum reference frame and your reservoir, we have some strong coupling on that point. Because this is an Hamiltonian that you can observe in the lab. So basically, you can use this Hamiltonian to perform this unitary on your joint system with the quantum reference frame and the reservoir. Those two lab chi are just projection into the total angular momentum. Sorry, the total angular momentum space of j plus 1 half and j minus 1. So actually, for those who actually understood this expression, this is pretty much look like a phase gate. It's actually in a larger space. And Oh yeah, so I guess I didn't put all the equation in those slides or all this, but anyway. So this defines actually your map chi, so it's an unitary that you implement, and then you can actually write this gate fidelity in terms of the moments, and then you can actually use theorem 2 to compute how those moments involve in the number of views, and then those computations are represented in this graph. I don't know how well you see, but the method 3 I talked to you about was the first line here. But it's a nice way, using those methods is a nice way of comparing different methods for example, implementing gates by using a point of reference frame. Okay, so this is just to say that the theorem 3 that I gave earlier is backed up with the example that I gave. The third example follow all the conditions that I gave with theorem 3, and actually it's SG square scaling. So V3 is actually that example. A, it's the line corresponding to A is actually corresponding to the measurement of the spin one-off to know if it was actually parallel to parallel or perpendicular to the n-axis. It also followed the function of theorem 3, and actually also scaled with G squared. Now we had two different examples that we didn't discuss that actually does not follow the function of theorem 3 and they double scale as like G squared. Okay, so here's we're going to conclude. First, and well, probably the most interesting part was that I provide actually a polynomial representation for maps that are covariant with respect to E-rems and SU2. And then we generalize the concept of quality function and introduce, well, the use of moments for point reference frame. And we give recursive equation. We simplify those recursive equations by using the previous representations. And we derive sufficient condition for the longevity of a point reference frame to scale by a factor proportional to the square of the dimension of the point reference frame. Thank you.